All right. Now, we've talked a lot about reactions. We're going to start putting that to use. Um, and our first step in this is thinking about combustion analysis. This is going to circle us back to when we talked about empirical formulas and hopefully remembering what an empirical formula is. Remember, that's our lowest whole number formula for a compound. And we saw before, it feels like ages ago now, but we saw before um, how to turn data into the empirical formula, okay? This relates to this as well, okay? This is another way to get data, but since we're talking about reactions, this is a way we're gonna do it. And a lot of times, if you're working in a place and you're making compounds and you wanna prove, maybe not prove, but you wanna, you know, figure out what the formula is and or make sure you got the right stuff, you can send it out for analysis and you'll get what's called a combustion analysis or an elemental analysis. And essentially what's happening here is that they take your sample and they put it in a pure oxygen environment and they burn it so that everything turns to a gas. Okay. And when they do that, it's essentially in a pure oxygen environment and they're flowing oxygen through it and they're burning it and all the gases are fired through this thing. Okay. This is just one variation of looking at it. There's a copper oxide uh, port, which will ensure that all of the carbon in the sample is converted to CO2. There's a water absorber. This is going to measure how much water comes out. There's a CO2 absorber that's going to measure how much CO2 comes out. Okay. And if you're looking for something besides carbon and hydrogen, uh, you can ask for those to be assessed as well. You can also figure out, request a molar mass for your sample at the same time. So all these things can go together to help you figure out a lot about your compound. Now, combustion analysis is great because it's going to lead us to the empirical formula. And if we also pay a little bit extra and get the molecular weight out of this, we'll also be able to get the molecular formula. Okay, so the way this is going to work is essentially the data comes out and what you get is how many grams of CO2 came out of your combustion and how many grams of water came out. Okay, and we're going to make an assumption that your compound started and had C, H, and O in it. Okay, oxygen is a hard one to test for, but we'll show you how to do it. Um, we can figure out we can figure out from grams of CO2, we can use molar mass to get moles of CO2, do the same thing for water. Once we have moles of CO2, we can figure out how many grams of carbon are in there, and the same thing for this, we can get grams of hydrogen that way. Once we have those, then we'll know how much sample we started with. We can subtract and figure out how many grams of oxygen is there. Okay, this is how we're going to get the oxygen from our CHO compound. Once we have the grams, every single one of those dudes will turn into moles because we have to get to moles to do a formula. Once we have all of our moles, then we're just going to get mole ratios and turn them into an empirical formula, which we can then turn into a molecular formula if we need to. I can't spell it, but we can say it, molecular formula. All right. So essentially, that's the process. Okay. I'm going to work an example with us, and this will give us practice with dimensional analysis, a little bit of introduction to what we're going to talk about next, which is stoichiometry. And we're also going to get reminders on empirical formulas and molecular formulas as we do this. All right. So we've got a sample. This sample that we know at the start has 18.8 grams. This is our total grams of sample. We do the combustion analysis and we get out 27.6 grams of CO2 and 11.3 grams of water. Okay, so we're going to work through this. Make sure I do this right. Okay, and the first thing we want to do is we're going to find the grams of carbon and hydrogen. Okay, remember what we said before, what we're going to do here is we're going to take our grams of CO2 or water. This will lead us to moles of CO2 or water, and the moles of CO2 will lead us to moles of carbon, which can lead us to grams of carbon. That's our step through there. Okay. Let's do it. All right. So we are told we're starting with, ouch, sorry, 27.6 grams of CO2. We always want to make sure we have units and we want to have formulas on stuff, especially because we're changing what the formula is as we're doing our dimensional analysis. Okay. We want grams to cancel, so we'll slap that dude on the bottom. Grams of CO2, molar mass, you can look this up or you'll be told, I'll usually tell you, that's 44.01 grams of CO2 for 1 mole of CO2. Okay. The next step, moles of CO2 to moles of carbon, is using the formula as a conversion factor. And we've done this before. 1 mole of CO2 will give us 1 mole of carbon. And using our periodic table, we can figure out that, whoops, 1 mole of carbon is 12.01 grams. 12.01 grams of carbon. Okay. We're going to set up, well, let me go ahead and write the answer out for this one. Doing all this, we're going to get 7.53 grams of carbon. Okay. We're not done yet. I'm leaving it with 3 significant figures because that's what I wrote down in my notes. We got it. Okay. We're going to do the same process and get grams of hydrogen. We're going to start with our water. So this would be 11.3 grams of water. 1 mole of water, we have to use moles and molar mass to get there, is 18.02 grams of water. Again, I'd give you the molar mass. Don't bother trying to calculate it out. Okay. Especially if I've given it to you, that's a waste of your time and space to get that taken care of. Now, 1 mole of water, remember it's H2O, so this is 2 moles of hydrogen. Once we have 2 moles of hydrogen, then we can say that 1 mole of hydrogen is 1.01 grams of hydrogen. This will give us grams of hydrogen. And as we math that out, we're going to get 1.26 grams of hydrogen. Okay. Sound good so far? Nothing too terribly shocking or new quite yet. Actually, literally, this is nothing new. The new thing is we're putting all these things together. Okay, so we got grams of carbon and hydrogen. Let's use those to figure out our grams of oxygen. So we're going to subtract. Our total mass was 18.8 grams. This is our total. Minus 7.53 grams. That was our carbon. Minus 1.26 grams. That was our hydrogen. And this gives us a nice 10.0 grams of oxygen. Okay. Cool. All right. Next. So now we have grams of C, H, and O. We need to get moles of C, H, and O. That'll be the next bit here. Convert everybody into moles. Let's do that and say 7.53 grams of carbon. Now, we could have paused ourselves on this step and taken here and written down moles of hydrogen and moles of carbon to do that. Okay. But you have to figure out, not hydrogen, you have to figure out both moles of carbon and hydrogen and grams of carbon and hydrogen. So I'm just doing it twice so we can see it. Okay. And I don't want to use that. Okay. So we're turning our grams into moles. So 7.53 grams of carbon. 1 mole of carbon is 12.1 grams. We're going to do the same thing for hydrogen, 1.26 grams of hydrogen. 1 mole of hydrogen is 1.01 grams. And then we have 10 grams of oxygen. That's from our subtraction from the last little bit here. Oh, excuse me. And 1 mole of oxygen is 16.00 grams of oxygen. Okay. All right, so we're going to math these out. What do we get? We've got 0.627 moles of carbon. We've got 1.25 moles of hydrogen, and we've got 0.626 moles of oxygen. Okay. All right, we've got our moles. Next thing we can do now is we're going to get mole ratios and figure out what our things are. Okay. If we look at our data, what we want to do is divide all our guys by the smallest one. The smallest one we have here is oxygen. So we're going to divide everybody by the oxygen moles. And I'm going to show our work over here. All right. So 0.627 moles of carbon divided by 0.627 moles. This will give us 1.00 for carbon. 1.25 moles of hydrogen, 0.626 moles from our oxygen. It's going to give us 2.00 moles of hydrogen. And of course, dividing our 0.626 moles of oxygen divided by 0.626 moles is 1.00 for oxygen. So that means our empirical formula for this is CH2O. Okay. Now, let's say we are giving ourselves a little bit extra and we want to figure out what the we want to figure out the molecular formula, and we've got the molar mass. We can do it. Remember that our molecular formula should be a whole number multiple of the empirical formula. So what we need is we have our molar mass, and we are going to divide this by our empirical formula mass. This is going to give us our ratio. Okay. Once we have our ratio, we can multiply our empirical formula by that ratio to get it. Okay. All right. Let's show our work and figure out our empirical formula mass. That's going to be, we had 1 carbon, so that's 1 times 12.01. I'm going to do this in grams. We have 2 hydrogens times 1.01 grams, and we have 1 oxygen times 16.00 grams. So this is 12.01 grams. This is 2.02 grams. This is 16.00 grams. We're going to add all those dudes up, and we got 30.03 grams. This is our empirical formula mass. This is our molar mass we were given. So our ratio is dividing those two things. You always want to divide the bigger one by the smaller one so we get a number that's bigger than 1. All right, so 180.16 divided by 30.03 gives us, what do we have here? 4 significant figures, 5.999, which is great. We can round this dude to, well, that's what we're going to say our final answer is for the ratio, which is really like 6. So if we say CH2O, and we're going to take this whole dude times 6, this is going to give us damn it, C6H12O6, and that's our molecular formula. Okay. That's how it works for combustion analysis. I don't usually ask a combustion analysis complete question on a test, but we should know how to figure out molecular formula and empirical formula. We should know how combustion analysis works. Okay. And just pay attention to stuff. If you need me, I am here. We can answer questions and work through stuff together. Okay. I will catch you next time.